Good afternoon, class. We are looking at practice test number 2, module 2, covering chapters 3 and 4. Here's chapter 4, exponential and logarithmic functions. Find the formula for an exponential function that passes through the point 0, 2000 to 20, where f of x is a, b to the power of x. So basically, as you can see, a and b are missing. You are given two pairs, plug in, and you find using two equations, two unknown, a and b. So if we plug in 0 and 2000, f of 0 is a times b to the power of 0, which is 2000. And if we plug in 2 and 20, we get f of t equals ab squared equals 20. Now, this is 1, a becomes 2000, and we put this into the general equation. And now we apply that to the second one, where it says ab squared is 20. So f of a 2 is a, which is 2000, b squared, which is 20. Divide both sides by 2000. B squared becomes 1 over 100. B is 1 over 10, and negative over 1 over 10. Exponential functions, the base must be positive. Negative 1 over 10 is out. So the final answer is 2000 times 1 over 10 to the power of x. Let's deposit $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it's compounded monthly? A of t equals p times 1 plus r over n to the power of nt. That's the compound interest. P is $10,250. R is 4% or 0.04. T is 10 years. And because it's monthly, n is 12. So plug in. So we replace the n with 12. We put this into a calculator. Gives us $15,281.03. We go with 2 decimals when it comes to money. How much will the account have at the end of 10 years if it's compounded weekly? At this point, n is 52. So into this formula, we replace the n with 52. We put this into a calculator. We get $15,288.85, a little bit more. How much will the account have at the end of 10 years if it's compounded continuously? We use this formula, A of t equals p e to the power of rt, same p, same r, same t. So 10,250 e to the power of 0.04 times 10, and that makes it, of course, 0.4. You use a calculator, $15,291.20. It's more because it's compounded continuously. What is the doubling time for this? As you know, the definition of a doubling time, that means the amount of time it takes for something, whether it's an investment or a population, to double in size. So if the initial value is p, now doubling means a of t will become 2p. Needless to say, you don't even have to know what this is. So p and p cancel each other. And now you can go either by the definition and change it from one format to the next, from exponential format to logarithmic format, or you might say, I'm going to take a natural log of both sides. The reason you want to take a natural log of both sides, because this has the base e. So if I put ln2, ln of e to the power of rt gives me that, and so we have ln2 divided by r, ln2 divided by 0.04, which is a little bit more than 17 years, so 17.3 2868. As far as the number of decimals, they normally tell you how many. Use the graphs shown to answer the following question. All have the format f of x equals a b to the power of x. Which graph has the largest value of b? Which one has the smallest value of b? First, let's remind everybody of this format. Y equals a to the power of x. A is larger than 1 exponential growth. Y is a to the power of exponent. A is between 0 and 1 exponential decay. And of course, as an example, you have 2 to the power of x versus 2 to the power of minus x. Please understand, this means 2 to the power of minus 1 to the power of x, which is 1/2 to the power of x, or 0.5x. So that's why we said it's between 0 and 1 here, okay? 0.5 to the power of x. Now, first and foremost, this is located at 0, 1, 0, 1, 0, 1, okay? Whereas this one, it's located at 0, a, y equals a, b to the power of x. Second, if you go back to this graph, when the base gets larger, the y gets closer and closer to the y-axis. So, which graph has the largest value of a b, the base, the one that is closest to the y-axis from the right side? So this one, this one, this one, clearly D is the closest. Which one has the smallest value? The one that is closest to the y-axis from the left. Now, if this is 0.5x, for example, 1/5 x goes like that. It gets closer, just like this one, right? And so in this case, it's clearly on the left side, graph C. On the left side, graph C. Which graph has the largest value of A? Which graph has the smallest value of A? Well, what is A? A is the y-intercept, everybody. So intercept takes place at 0, A. So which one has the largest? Look at the y-intercepts. Obviously, this is the largest y-intercept. So graph C. Largest A or y-intercept is this point, graph C. What about smallest value of A? That means smallest y-intercept, which is this point. See, look at the y-axis, this point, and it's on the graph of what? F. Use transformation of the graph of f of x equals 2 to the power of x of the function below. State horizontal asymptote, the domain, and the range of f of x equals 2 to the power of minus x. So what do we do first and foremost? We should know the graph of 2 to the power of x looks like this. That's one of those essential functions. With the y-intercept located at 0, 1. Now we want f of x equals 2 to the power minus x. X changes to minus x. That means reflection with respect to the y-axis. Looking like this. And 0, 1 still has the same location. In essence, now, of course, this is 2 to the power of 0, 1, and this is y equals, or f of x equals 2 to the power minus x. So as you can see, we have the same y-intercept, we have the same horizontal asymptote, we have the same range, we have the same domain, except this is increasing, this is decreasing. That's the difference. Therefore, f of x equals 2 to the power minus x. Horizontal asymptote remains as the x-axis, which has the equation y equal to 0. Domain, all real numbers, range, the same. What about g of x equals 2 to the power of x plus 1? Well, we are going to go back to this and we're going to shift it up by this much. So shift it up by 1 unit. So when you do that, the effect is that your horizontal asymptote is no longer the x-axis, but rather it goes up. So now the horizontal asymptote has changed to y equals 1. The y-intercept of 0, 1 has changed to 0, 2. So what's the effect? Domain is all real numbers. However, the range is from 1 to infinity, and horizontal asymptote is y equals 1. Consider the function f of x equals 4 to the power of x. Write a function that results from the given transformation. Shift f of x 3 units up. So just add 3. Shift f of x 5 units left. 4 to the power of x plus 5. Left plus 5. Right minus 5. Reflect f of x. And notice all of them go back to original function, not that we do it to this one or this one. Original function. So reflect it about the x-axis. So you put a negative in front of the function, so it becomes minus 4 to the power of x. Reflected about the y-axis, you put a negative in front of x, so you get I of x equals 4 to the power of minus x. The graph is a transformation of y or f of x equals to the power of x. Write an equation for the graph. So notice what you have. Look at two things. Look at the y-intercept and look at the horizontal asymptote. The y-intercept is located at 0, 2. Horizontal asymptote has the equation y equals 3. So if we start with the basic function y equals to the power of x, which looks like that, with the y-intercept of 0, 1, there seems to me that this is some sort of a reflection across the x-axis, so that means you put a negative in front of that. So y or g of x equals minus 2 to the power of x reflected across the x-axis, make it look like that. And that means now your y-intercept has coordinates 0, negative 1. Again, we're going to compare. We notice that this one shifts up and 0, negative 1 goes to 0, 2, which means it shifts up by 3 units. Shifts up by 3 units. So now this one has the horizontal asymptote of y equals 3. And the y-intercept of 0, 2. And the formula is h of x equals minus 2 to the power of x plus 3. If b is larger than 0, meaning the base, sometimes you use a, sometimes you use b, and b is not equal to 1, y equals log x base b is equivalent to x equals b to the power of y. When you look at this one, you notice that they both have the same exponent, the same base. And if you look at this one and follow this arrow, log x base b equals y means b to the power of y equals 6. So for a general case where y equals log x base b, then b to the power of y equals x, we have the following properties. Log 1 with any base is 0. Log b base b is 1. When the base and the argument are the same, the answer is 1. All of them you can go with the arrow, including this one. Log base b of b to the power of x is x. B to the power of log base b of x equals to x. These are because the two functions are inverse functions. Product rule, log x y is log x plus log y, same base b. Quotient rule, log of x over y is log x minus log y base b, and all of them base b. Log of x to the power n is n log x base b, and this is the power rule. All of them have the same base. Now, if we go to common log, where the base is 10 log x base 10, we don't write the base, we simply say log x. That means 10 to the power of y is x, and we can see those properties. Just as an example, log 1, you don't have to write the base, but why is this log 10? Because these two must be identical, and you can see the rest of it. In the case of a natural log, we don't write log x base b, but rather ln, means the base is e, and we can see that again. For example, number 2 says the base and the argument must be the same, so this must be ln e equals 1. Logarithmic functions and exponential functions are inverse functions, so y equals e to the power of x and y equals ln x are symmetric with respect to the line y equals x. Change of base formula. Log x base b is log x over log b with any base, for example, a. Obviously, we're going to choose either 10 common log or e natural log because we can calculate now the answer using a calculator. We can estimate it. If you do the cross product here, you get log b base a times log x base b is log x base a. It's just a cross product of this. Also, ln x is less than 0 when x is between 0 and 1. It's 0 when it's 1, and it's larger than 0 when x is larger than 1, meaning the ln x is this part, everybody, is below the x-axis. This point is 1, 0. This portion is above the x-axis. That's what they're referring to, those 3 parts. Let's rewrite each equation in exponential form. The arrow tells us 5 to the power of q is m. The arrow, remember, ln, the base we don't write, is e to the power of z is v. Common log, the base is 10, we don't write it, 10 to the power of t is w. Going back, you can follow the methodology of going from log to exponentials and vice versa. For this one, we're going to say log y base 3 is x. For this one, log h base e, that means ln h is k. For this one, log b base 100 is a, and we're done. So we should be able to go back and forth easily. All right, we want to graph log of x minus 7. So we state the domain, vertical asymptote, and the end behavior. We start with the basic function y equals log x, which looks like that. And of course, the x-intercept located at 1, 0. Log x, remember, the base is 10, which makes it larger than 1, so it looks like this. So what is the effect here? X minus 7. So we are going to shift log y equals log x to the right by 7 units. When we do that, it creates this graph. So the x-intercept, which was located here at 1, 0, now goes to 8, 0. And the vertical asymptote, which was the y-axis, now it's x equals 7. All you have to do is set this one equal to 0, and you see that. So what is the effect? Please understand the range doesn't change, but the domain is from 7 to infinity now. The end behavior as x approaches 7, x goes to negative infinity, and as x approaches infinity, f of x goes to infinity, the first quadrant. But what I want to make a point of over here, really, it's 7 from the right. This notation means 7 from the right, like 7.1, for example. If I put negative, that means 7 from the left, like 6.9. Okay. In a limit, that means really from the right is 7.000001, a lot of zeros and then 1. So to the right of 7, that's the meaning of it. All right, to graph this, we start with ln x. And of course, we have the same x-intercept at 1, 0. Then I want to discuss minus x. So ln of x to ln of minus x. You're changing x to minus x. That is reflection across the y-axis. So this becomes that. Therefore, this was at 1, 0. Now this is negative 1, 0. I'm going to go back to this because I discussed minus x. I'm going to take the negative sign out, and I'm going to write it as ln of minus the parentheses x minus 2. And that clearly says, let's shift it to the right by 2 units. So we are going to shift this green one to the right by 2 units. When we do that, what happens is that this negative 1, 0 goes back to 1, 0 again. Also, the vertical asymptote is x equals 2. And by the way, you can set this one equal to 0 or this one equal to 0, and you see vertical asymptote is x equals 2. So the result is that the range, if you look at all of them, hasn't changed, but the domain for this guy is from negative infinity up to here. That means to 2. So domain has changed, range hasn't. What about the end behavior? As x goes to 2, g of x goes to negative infinity. That means this one, vertical asymptote, as x goes to negative infinity, y or g of x goes to positive infinity. And again, I want you to see that this one is to the left of number 2. So 2 from the left. Again, as an example, 2 from the left is like 1.9999. That's the concept. And this is the notation which is used in calculus. So 2 from the left. All right, the function this time is h of x equals minus log 3x minus 4 plus 3. We want to do the same thing. We want to do the transformation and state the domain, asymptotes, and so on. So we start with log x, looking like that, 1, 0. So the very first thing we do, we look at 3x, so log of 3x, which means there's a horizontal shrink by a factor of 3. And if you look at this graph, so this one was located at 1, 0, and now it's located at 1/3, 0. And here's the simple reason. If you plug in 1/3 here, the product becomes 1, and log of 1 is 0. We're going to go back to see what's the next step. 3x minus 4, we're going to factor the 3 out. So we notice that it shifts right by 4/3. So the same thing now shifts right by 4/3. So when that happens, class, remember this one had the x-intercept of 1/3, 0. So if we go to the right by 4/3, we're going to add 1/3 to 4/3, and we get 5/3. So that would be the new x-intercept in this case. The next one, we are going to apply the negative. So if we put the negative in front of it, that means it's going to flip over with respect to the x-axis. And when that happens, the x-intercept still has the same location. And finally, we are going to add 3. That means shift up by 3 units. So when we shift up by 3 units, what happens? You get this. You can write the same thing, or this one plus 3, they are the same class. Okay, this one and this one are the same. So shift up by 3 units. So this point goes up by 3 units. So 0 plus 3. So 5/3 comma 3. That's how you manipulate this point that we had in the first place. Now, to really better understand this, I want to look at the graph by itself. I want to look at the final result, the green graph by itself. So this is 5/3 3, and it looks like that. So here's 5/3 3. And the vertical asymptote, you can even set this equal to 0, this one equal to 0, x equals 4/3. And so we should notice that the range hasn't changed. It's still our real numbers, but the domain goes from 4/3 to infinity. Of course, 4/3 is not included. As far as the end behavior, when x goes to 4/3, h of x goes to infinity. When x goes to infinity, y or h of x goes to negative infinity. This one, please understand, which side of 4/3? From the right. So x approaches 4/3 from the right. That is the proper notation we use. Expand each log as much as possible. Well, for part A, we go with the product rule from left to right. So this is log of x plus log of y plus log of z, and all of them have the same base 7. This one, we're going to use the quotient rule, ln of the top minus ln of the bottom, ln 9 minus ln x. This one, we use number 7, the power rule. 10 becomes the coefficient. This one, you can do it in 1 or 2 shots. So if we were to do it in a couple of steps, we would get log base x of a squared b to the power of 4 minus log base 7 of c to the power of 7. And this one is log base x of a squared plus log base x of b to the power of 4. And now each one, the exponent becomes a coefficient in all cases. So 2 log a base x, 4 log b base x, minus 7 log c base x. That's what happens. Well, we want to expand, and so we start writing this as log of x cubed plus x cubed y to the power of 5 to the power of 1/2. This becomes the coefficient, and you write 1/2. log of x cubed plus log of y to the power of 5. So 1/2 sits in front. Okay, so the order wasn't right, class. So let me just, so basically this one, write it here. So 1/2 log of x cubed plus log of y to the power of 5. And then this becomes the coefficient. This becomes the coefficient. Apply the 1/2, and you get 3/2 log x plus 5/2 log y. A part B is ln of the top minus ln of the bottom, and it can't be simplified, so ln x minus ln of x squared plus y squared. Now this one. It's log of the top minus log of the bottom. This one, x to the power of 1/2. This one, 10y to the power of 1/3. And we can put the 10 in front here. We can separate these two into log base 4 of x to the power of 1/2 plus log of 10y base 4 to the power of 1/3. Now, clearly, 1/2 becomes the coefficient. Same thing here. And this one, you separate them into log 10 plus log y. So what do we end up with? 1/2 log x base 4, 1/3 of log 10 base 4, 1/3 of log y base 4, and the last one is the last one, minus 10 log base 4 of z. So this is the composition completely. We want to condense and bring them back to a single log. That means we want to combine this, and we go with number 5, and we go from right to left. You just multiply these two, you get the product of the two. So log of 6x to the power of 9. Whereas for part B, you go with the quotient rule, number 6. And you say it's ln of 6x to the power of 9 over x squared. You simplify it to ln of 6x to the power of 7. For part C, we go with the power rule first. Again, we are going from right to left. And then we go with the product rule, number 5, and we say log of x squared times x plus 1 cubed. We are done. In some cases, they may want you to multiply them through. I don't want you to do that, but if in case you're doing the work they ask you. All right, for part D, we are going to put them together. So let's see what we do. First and foremost, we are going to get rid of this, put it here, get rid of this, put it here, and we're going to put this next to this so it becomes clear what we are dealing with. So this is log x, this is log z cubed, this is minus log y 1/2. So this is log of x z cubed. And then what? Log of x z cubed over this. And y to the power of 1/2, by the way, everybody, is square root of y. And that's the final answer. Log of x times z cubed, because this has a negative, goes down, divided by square root of y. We want to solve exponential rules, exponential equations. And when we look at part A, we have the same base. We must have the same exponent. According to these rules, you have the same base, you have the same exponent, you have the same exponent, you must have the same base. And therefore, minus 4x minus 3 must be equal to minus x. So you move the negative 4x, you add it to the other side, 3x divided by 3, and you get negative 1. Part B, 64 can be written as 4 cubed and 16 as 4 squared. The left side, using the power rule of exponential, gives you 4 to the power of 3 plus 3x. And because the two sides have the same base, they must have the same exponent. That means 3 plus 3x must be 2. So what do? We move this to the other side. Minus 3 and 2 is negative 1, divided by 3. X becomes negative 1/3. Two e to the power of 3x is 13. We are going to divide by 2. And now you have a choice. You can change from exponential format to logarithmic format. Or you can say, I'm going to take a log of both sides. Because the left side has a base e, I'm going to take a natural log. So the left side is 3x. And the right side is ln of 13 over 2. I'm going to divide by 3. And this is the exact answer, everybody. Always write your exact answer. And then this is the approximation, however many decimals they ask you to put. If you want to solve this, you can solve it just the way it is, or you can choose e to the power of x to be some variable such as, let's say, u, then this would be u squared. And this is factored into u minus 3, u plus 2, or just factored in this format. Makes no difference. You can do it factored directly. You can do substitution and factor it. The first one says e to the power of x must be positive 3. The second one says must be negative 2. And it can't be negative, or it can't even be 0, because the range is 0 to infinity for exponential functions. So obviously, again, you can take the natural log or rewrite it in logarithmic format. X is ln of 3 this is the exact answer again. Okay, you should always include your exact answer, and this is an approximation. We want to solve a bunch of logarithmic equations. If you have a log and a number, make sure you bring all the logs to one side, all the numbers to the one side. And so this, all you have to do, there's not much you have to do, just go with the definition. 9k is 3 squared, or 9 divided by 9, the answer is 1. The next one, you have a couple of logs on the left side and a number to the other, so we're going to bring the left side together by using the product rule. So log of 4 times minus 5x, meaning log of negative 20x is 2. And now the definition, remember there's no base, that means base is 10, right? With log, so 10 to the power of 2 is minus 20x, which means 100. Divide by negative 20, and you get x equals minus 5. Now, you must check. If you put minus 5 here, you get positive 25, it's fine. The way I would check, I would make sure that none of the arguments is 0 or negative. Make sure they're all positive. Now, what about these two cases? Number one, this one, both sides have the same log. They have logs with the same base. They must have the same arguments. We're going to move things around. Ten n equals 10, n equals 1. Now, what about the next one? One side has a single log. The other side, the right side, doesn't. So we are going to put these two together, again using this product. We're going from right to left. And now each side has one log. They have the same base, namely 10. They must have the same argument. So x plus 12 and 12x must be the same. Divide by 11, and x becomes 12 over 11. ln of x plus 4 minus ln x equals ln of x plus 1. Both sides have nothing but natural logs. The right side is just 1. The left side, we bring it into 1 by using a quotient rule. So the left side becomes ln of x plus 4 over x. They have the same base, namely e. They must have the same argument. And we do the cross product. So we get x plus 4 equals x squared plus x. Drop the x. X squared is 4. X is plus minus 2. We check the 2, 2 plus 4, 2, 2 plus 1, everything is fine. Check the negative 2 is fine here, not fine here. You get rid of it. Because makes this argument negative. You don't even have to check further. As long as one argument is negative or 0, it's out. To do part B, we are going to go with number 5, and we bring it into a single log base 2 of x times x minus 1. And now we go to the definition of a log. X times x minus 1 is 2 to the power of 1. Left side is x squared minus x. Move the 2, make it x squared minus x minus 2. Simple factoring. X minus 2x plus 1. We get two answers. X is either 2 or negative 1. We put the 2 here, it's fine. 2 minus fine. We put the negative 1, it doesn't work here because the argument can't be negative. You don't even have to check the next one. That's out. Four to the power of x plus 10 equals 3. Obviously, you are going to move the 10. Four to the power of x can't be negative or 0, therefore there is no solution. And again, remember, the range of basic exponential functions is 0 to infinity. Now, to do part B, it's something interesting. The right side is 1. The left side has a base 7. And you know a number to the power of 0 is 1. And because the left side has a base 7, write it 7 to the power of 0. 1 is the same as 7 to the power of 0. Now the exponents must be the same. And x becomes 10. In the case of part C, we want to come up with the same base. We can't. We want to come up with the same exponent. We can't. So when you want to solve for a variable which is part of the exponent, you have to take a log. What type of log? Well, if any side has 10 as a base, common log. If any side has e as a base, natural log. Since they don't, it doesn't matter. So let's go with one of them, natural log or common log. Now, x becomes the coefficient, x minus 2 becomes the coefficient. Please understand x times ln 4 is like, 2 times x, 2x. So this is a number. So multiply these two, multiply these two. And now, since we are solving for x, anything involving x comes to the same side. So move this one, make it negative. Factor the x out. Divide by the parentheses. And that's your exact answer, everybody. Now, what I want to mention, if somebody says the answer is 2 ln 9 minus ln 9 minus ln 4 is just as good. I want you to see why. If we had moved this differently, okay, for example, this one to the right, this one to the left, it would give us this. Or if you multiply negative by the denominator, you get minus ln 4 plus ln 9. Also, over here, if we used log, all of this would be log, and the ratio would be the same. So 2 log 9 over log 4 minus log 9 with a negative alpha. Assume log 2 base b is a, log 3 base b is b, and log 5 base b is c. We want to evaluate log 50 base b and log of the fifth root of 300. You have to factor the numbers such that they involve the numbers that are given 2, 3, and 5. I hope you know 50 is 2 times 25, therefore 2 times 5 squared. So this is log of 2 plus log of 5 squared. And 2 becomes the coefficient. And now you can say, well, This is A, this is 2 times C, and you're done. We're going to do the same thing here. First, this is 300 to the power of 1/5. Second, 1/5 becomes the coefficient. Now you have to cut it into pieces that it has nothing but 2, 3, and 5 as factors. So I want to remind you of a couple of things. Prime numbers, 2, 3, 5, 7, 11, 13, 17, 19, 23. It continues. We want to do prime factoring of 300. Divide by the first prime number, in this case 2. 152, 75. Can I divide by 2 anymore? The answer is no. We got 3, 25. Can I divide by 3 anymore? No. 5, 5, 5, 1. The moment we hit 1, we are done. So we're going to write it as 2 squared times 3 times 5 squared. So 1/5 remains. This is log of 2 squared plus log of 3 plus log of 5 squared, all of them the same base b. Log of 2 squared is 2 log 2. This is log 3. This is 2 log 5. All of them have base b. And replace this with a, this with b, this with c, and you're done. A nuclear reactor contains 200 grams of radioactive plutonium, and plutonium decays according to this formula. A equals A sub 0, e to the power of negative 0.0000284. For exponential growth and decay when it comes to application, it's in this form for the decay. N of t equals n sub 0, e to the power of minus kt. Even if you use positive kt, you end up working it out such that ultimately you have to have a negative number here. That means the exponential decay. So what is given? A sub 0 is 200 grams and t is 5,000 years. That's what's given. So plug in, replace the A sub 0, replace the time, put it into a calculator, and it gives you $173, 173.52 grams. So 200 grams goes down to that much in over the course of 5,000 years. Find the half-life. By definition, half-life is half of the original size. You don't even have to put the 200 there. So A sub 0, half of A sub 0. We've done that in lecture, but I'm reminding you. So A sub 0 cancel out. You get 1/2 on the left side. Now you can take a natural log of both sides, or like I said, go to the definition of a log versus exponential. So if you take a natural log of both sides, the left side is ln of 1/2, or ln of 1 minus ln 2, and the right side is just the exponent. Now ln 1, you should know is 0. So what is t? T is minus ln 2 divided by this number. Put it into a calculator. Results in 24,406.59 years. Again, normally they tell you how many decimals. And I want you to know that the continuous rate of growth is R. That R that we have, or K if you will, this is called K or R. That is called the continuous rate of growth, or in this case, continuous rate of decay.